Hello engineers. So the main purpose of this video is to motivate you to apply your Verilog knowledge and design a CPU, a 32-bit CPU. And also not a very simple CPU, but a CPU which is actually inspired, but which is actually inspired from ARM LRM, which is freely publicly available. So we will take some inspiration from them and some from our own knowledge, and we'll try to build something which is simple enough to design in 10 hours of your coding, and also not so simple so that you don't learn anything. Welcome to my channel. Those who don't know, myself Rasdeep, and I'm a vlsi engineer currently working in vlsi domain. So in this channel we keep on making videos related to vlsi industry only, and from last few months I was not very active in this channel. But why? Because I was developing something which is very much important to me and probably important to you, and that is my web portal, which is whyRD.in. So in whyRD.in we have a lot of courses, and I thought, let me do one thing, give you something for free so that you get motivated enough so that in future you can buy something. Okay, so we will start with week 1. We will see all the videos of week 1, and then we'll discuss again. Get start from the introduction. Hello guys, welcome to this course of creating your own CPU using Verilog. So as name suggests, this is not a course to learn Verilog. Like if you haven't done anything on Verilog previously, then probably this is not your course for now. You need to get the prerequisites. We'll discuss what are the prerequisites, and then you can make best use of this course, right? Also, if you have the overview, for example, FSM coding in the Verilog, you have the overview, but probably you have done 1 year ago, you just forgot, then it's a good idea to recall them. Or else I also try my best to recall few things anytime I get the chance, but I won't be recalling everything from scratch because we have the time limitations. It's a very short course of 4 weeks only, and as it is a advanced level course, so we need to respect others' times also. We can't explain everything, so better would be that you should get the prerequisite. From where you can get the prerequisites, there are free resources are available. In the NPTEL also we have a course in I think you can search in YouTube just Verilog IIT Kharagpur, then you will get a very nice course there. Actually I learned my Verilog from there only, so you can go there. It's a free of cost course. Also you can refer to my course. I have few courses where I try to make you learn Verilog using the practical, like you will code the Verilog there. We have one portal called HDL Beats. So in HDL Beats there are series of questions. Questions start from level 0 to expert level. I won't say expert level, but yeah, till the level from where you can easily continue with this course then. So you can go to whyRD.in. So there you can see 2 courses are there, part 1 and part 2. You can go through part 1, part 2 quickly and get the prerequisites. So in the prerequisites we have, as usual, for sure we will be having the digital electronics. We need to know about digital electronics. And in digital electronics, what is combination circuits, what is sequential circuits, what is your FSM. FSM means final state machines. So those theoretical knowledge you must be knowing, right? And after that you must be knowing the Verilog codes of those also, right? How to Verilog code your FSM, how to Verilog code your combinational blocks, what are the different style of Verilog coding. We have different style, like we can go with behavioral model, we can go with data path model, or we can go with gate level also. So what those things mean? So those things also need to be required style of Verilog coding. Then anytime you design any things in real life using Verilog, that time we have a concept of which is called your data path and controller. And we actually most of the time data path and controller are joined together to get the final product. You need to know the concept of these two things, what these two things mean. Again, in that NPTEL course, in the later part of the course, they have actually defined those things. It's nicely explained there. Also, if you want to personally practice few questions before coming to this course, because here this course will have lot of codings, right? So if you have never done any coding, you might get afraid of coding those big programs. So better would be you just go to the Verilog practice part 2. You will find in my website whyRD.in. So there you can go there, and there actually we have the minor projects. 2 minor projects are there. So those minor projects are actually exploiting these things only, your data path and control path, both two. Also there is a minor project 0, you can say, or actually there was a question in HDL Beats. We did that question also in depth, and there I have explained nicely about this theory, what is data path and what is your control path. I won't gonna explain again. I said timing constraint. So please go through these things. So these are a rough prerequisite you must need to have to enjoy this course. So for week 1 content, you don't need any prerequisites. You can understand what is happening. But from week 2 onward, you need to have those knowledges. So if you don't have, then after week 1, just pause this course and get the prerequisite. Finish your Verilog part 1, part 2 if necessary, or that NPTEL course, and then come back here again. And also I forgot one prerequisite, and that is a little idea of test bench design, because we're gonna do a lot of coding and then we need to verify those, right, if they are working or not. Again, in my Verilog part 2, I have discussed about test bench there. You can get idea of test bench from that NPTEL course also. So in this course, our main objective is to design a 32-bit processor. Now your processor will do some arithmetic operations like addition, plus, minus, some logical operations like branching, if, else, right? If you have written any type of programming in your earlier days, you might know that in our programming we have a lot of branching instructions, if, else. So our processor should have the capability to do those things. So you need to design your ALU. We will discuss in detail. You need to design your logical unit, right? You also need to design the instructor registers, right? Also the decoder part. So why this is required? Because anytime I say add A, B, our computer never gonna understand what does add means, or what does A plus B means, or if add A plus B is there, then what steps are required. So we need to have some decoder there. First of all, we need to design a register, right? Instructor register, and then the decoding part. So those also we detail, like in detail we'll go through. We'll write the code, we'll try to execute them to see if it is happening or not. We also see the theory behind those, everything for ALU also, for logical one also, what's the theory. In instruction, actually we have different type of instruction, like loading instruction. You're gonna load from immediate or from a register or from the output IO pins. You have the shift instruction, you have the branching instructions. So we're gonna discuss everything in detail in this course. After that, the main part is that we need to design the data path, or first of all we need to identify what is data path to design that processor. So we will have a data path and we will have a controller. So we need to design the controller part also. Actually, I have a good analogy between your data path and controller. So data path, if you go in corporate area, so in corporate there are lower level engineers, right? Those are freshers, 3-4 years of experience, and then we have the managers. So those low, like it's very rough analogy, don't go word by word, but in rough. So those low level engineers, you can say they are data path. Data path, the main things of data path is to do all the things. Like I have given an example, add A and B, right? So to execute those add A and B, the circuit which we will have will be mostly comprised of data path, or the circuit which we will design, right? So that circuit will call as data path circuit, because it is doing something with data, some processing it is doing, right? But now the problem is that if in a corporate you have only junior level engineers and nobody to control there, so they don't have the visibility, right? They are doing the addition, add A plus B, but they don't know the bigger picture, why they are design like adding at A and B. Probably they are doing A plus B to actually execute one of the AI algorithm, because in AI algorithm, why I am taking AI algorithm, because all are interested to know about AI, so that's why I am bringing AI. But in any simple algorithm also we have addition a lot of time, right? But those junior level engineers, they don't have that visibility, why we are doing A and B, how much time we have to do A plus B, or when gonna I get that data in my A and data in my B, so that I start adding them. Because if in the exact moment I don't add, probably A and B have some junk value, and if I add those, I'll get a junk result, which is not the intention, right? So therefore there should be some controller which gonna control those execution. Or in our corporate arena, those junior level engineers must have some control people who have the visibility, like, hey, for doing this task you have only 1 day, hey, we got something from client, you do this work now only. So you getting the analogy, right? So those managerial people, you can say they are the controller in your digital circuits, And the junior level engineers or any engineer who are executing any jobs, they are like data path, right? So in our CPU also, or in our processor also, we need to identify those, and there we need to design a controller. So deciding those go hand by hand, and it's very interesting. So we're gonna have a huge interesting weeks ahead, so be prepared for that. After we would be designing our data path and control path separately, other things separately, right? Then we need to integrate them. So that episode gonna be very interesting. We'll integrate them, and the more interesting part would be that we'll also design a test bench to execute those two, and or probably we'll write a small code. I'll go what is code means. I'll go in brief, but yeah, this is also a prerequisite. You must have a brief understanding of, yeah, if you know Verilog, you need to have the coding part, right? So this is assumption that you know coding, but not high level coding that hey, you are applying for Google or Meta or anywhere else. Basic level coding, if else, function, how to handle functions, those things. Very basic level coding is required. The coding knowledge required for knowing the Verilog, that much is sufficient. So in test bench, we will try to write a small code and we try to execute in our CPU, and that is the work of your CPU actually. Anything you are seeing here, like you are seeing this in YouTube probably, or probably if you download it, how you'll see my video, you'll see my video in VLC player, right? Mostly. So this VLC player is actually a program. Somebody has written some instruction in the behind, and those instructions are being handled by your CPU currently, if you are seeing in downloaded form. If you are seeing in YouTube, probably the server of YouTube, which is a CPU only, right? Like there would be GPU, there would be NPU, other things, I'll go there later. But yeah, there would be some processor, right? Those are doing some instructions. So our test bench will be designing mostly in the last week of this course. So that time, this would be very interesting. We'll write some code and we'll try to see if the processor which we have, our child, right, which we have designed, can handle that code or not. So if you have already subscribed to this course, thanks a lot. If you haven't, then I will invite you to subscribe to this course. This course is gonna be very interesting, and for sure you will have a good project to show in your CV after the end of this course. After this course end, you can earn a certificate, and probably you can show in your LinkedIn, and you can just say, hey, I have done these things. So to get a certificate, you have these things you need to complete, and that is, first of all, very important, you need to complete the 75% of the course content. And then after every week, most probably for this week also, you will get a quizzes. So you need to finish those quizzes, and in those quizzes you must be scoring 75% and above. That is very requirement, because then only I'll be knowing that you are seeing my videos and you are understanding what is going on. Also very important, and which will really help you a lot for sure, and that is, you must upload the things you're gonna make, the processor, everything, in your GitHub. Don't worry, I will help you. If required, I'll guide you how to do that, but you must be uploading in GitHub the full projects, right? And probably then only you can write it in your CV, or probably you can provide the GitHub link, and then the recruiter can easily see that what you have done. I will tell you how to actually do that. Like you should add some specialty there. It should be different than the other, right? So I'll help you there. So that is must. So these three things you must be doing. There is another thing actually, and that is these questions. Why we don't finish an online course? There are some survey, and in survey it is been seen that mostly if it is a free course, then 5 to 10% people only finish that course. In NPTEL only there is a lot of example, because it is free, so you also might have the experience. If it is a paid, then probably it is 20 to 30% people finish that course. And actually I was seeing a great video from founder of Grade Up, I guess. Yeah, so he was actually mentioning one thing, and that is, if you are doing anything offline class, then most probably we finish that workshop 90 to 100%. But if it is online, then it's reduced 30 to 20% if it is paid, right? Why it is happening? Because if it is offline, then you have a commitment. If you are not going to the course, probably your parents will say, hey, why you are not going? Your friends are knowing that you are going for your coaching institutes. So if you are not going there, then your friends will tell you, hey, why you are not going? So because you have the commitment, other people know that you are taking that course, so you go there and you attend it. And by this, actually you are getting benefited, because you finish the course workshop and you get the knowledge. But in online arena, this is not happening. You are registered for this course. Probably the best friend of you also don't know that you have registered for this course. There is no commitment. So I'll suggest you, this is just optional. It's up to you. You can share today only after this video in your anywhere, like in your WhatsApp status or anywhere, probably in LinkedIn also, that hey, I have registered for this course, and probably in next 90 days I will have a GitHub link. So be ready to see my GitHub link and give me feedback if my processor is working or not, or how can I make it better. So this will give you a little bit of commitment, right? Because those people who have seen or reacted to your status, they might come back to you and they say, hey, it's already 90 days, why is your projects? Then so you are getting the idea, right? Also probably every week, after every week video, or after 40% 50% completion only, you can keep on sharing the detail what you are getting from this course in LinkedIn. And it's a very great idea to start actually writing your content in LinkedIn, and that is a nice way to increase your network, right? So I'll highly suggest you do one thing, and that is first that announce that you have doing something anywhere you like. Best is in LinkedIn. And then after each stages, for example, you have designed your ALU, then you can write a big content in LinkedIn explaining what you have learned, probably handwritten notes there. It will help you only because you are getting the commitment, you are doing something for outside world, so you will try to be perfect. And when you try to be perfect, therefore you are knowing more bits and pieces of that knowledge, right? Also this will help your friends because they will getting that knowledge, and probably they get motivated to take some other courses, or they might share you with some other resources where they have got the same thing in some better way, right? So that is a recommendation. So what is a processor? In layman language, processor is nothing but something which will process something. Your data, you will provide the data and it will process that, right? If it is in computer, it would become like a CPU, you can say. So it's a digital circuits which can process your data. You will give some input and it will give you the result. That is the simplest answer to these questions. Now, there are a lot of things, like currently in our computer, we have CPU, we have GPU, we have NPU, sometime we have TPU, probably we have heard of. And you might get confused that, hey, this is a course of designing a processor, and what we gonna do? Because all these four things are your processors only, because they are processing your data, right? Now, in this course, actually we're gonna design something which is called general purpose processor. And actually this general purpose processor are only called your CPU, central processing unit. Now it would be very nice to know a bit about these things, or if we can differentiate between this CPU, GPU, and NPU. You are taking this course, your friend asks, hey, what is difference between CPU and NPU? And if you can't answer, then they might laugh at you, hey, you are taking a course and you don't know. Therefore you can give this answer, and that is, see, as name suggests, this is a general purpose computing, right? So which means CPU can do most of your work, most of your general work we have, and which also means the work which your GPU can do or your NPU can do. For now TPU let's ignore, because actually NPU, TPU are like intermediately used, they are same only. This work can also be done with a CPU, because CPU is a general purpose computing, right? And if you go a bit specialized side, then that CPU will become your GPU. Now what's that specialized one? The time when GPU are invented, that time actually it's invented because in the name only we have the graphical processing unit. So it is mostly developed to process the video, to render the video, because in video, anytime you are seeing a video, what is actually doing your processor? The main purpose, the main work of your processor, what? It should encode those bit stream, because you are receiving bit stream only 101001, right? So it need to encode, not encode, actually decode. It need to decode those bit stream to color, right? You are seeing red, you are seeing blue. It need to decode those, and it need to identify the pixel, in which pixel which color should go. So, and that is called your video rendering. And they are actually a very simple work only, simple things only, but that simple things need to be done again and again. Same thing can be done using a CPU, very easy. Probably currently you are seeing my video in YouTube, yeah, server are there, but in offline mode if you see, then these things can be handled by CPU only, right? As I said, right, the work done by GPU can be done using CPU only, because CPU is a general purpose computing, right? So therefore the question is that what's the need of GPU? The need of GPU arises when you are doing something intensive. For example, you are editing your video. So editing a video, if you have done any time, you have a lot of cards, you have a lot of layers of video, right? Then you have to render it. So that time actually we need GPU. We can do the same task using CPU for sure, but it might take some more time. For example, you want to render your 4K video or 8K video. If you have only CPU, then that video might be freezy, or you might see there might be some frame drop. But if it is a GPU, then it would run very perfectly, because CPU, as name suggests, is designed for general purpose things, right? It is not focused on something only. So if you are focused on one work only, then you can do that work perfectly. But if you are focused or you are doing lot of things together, then you are not expert on anything, right? Same is the thing with CPU and GPU. GPU is the expert of rendering your video, playing during you play games. So that time also there are a huge requirement of those pixel selection, giving the color, those algorithm or those mathematical operation to be done again and again. So therefore GPU has been invented, and GPU got popular, become popular more when we have the cryptocurrency. So in the cryptocurrency also we find out that, hey, in the algorithm we have the same mathematical calculation which we are doing for our video rendering. So therefore for cryptocurrency mining also GPU got popularism. Also in the AI processing, because in AI also we do the same algorithm mostly, and we are doing the things in parallel, and actually GPU can process things in parallel. CPU mostly do sequential things. So if you give lot of instruction, it will take some time, but it can do all the work. It might take time, but it can do all that work. But your GPU are a little focused, right? Now the question is that, okay, GPU is focused, and what is NPU? So NPU is little more focused. So if I roughly create something, a visual diagram, so if you say this is the work boundary of your CPU, then this would be work boundary of GPU, a little focused, and then the NPU would be more focused. So what that focused area? So NPU, as name suggests, it's a neural processing unit. Neural means it's work for the AI. So in AI we have neurons like that. I am not gonna go there. If you know about it, it's great. If you don't know, it's also great, not required. So to process these neurons, right, just ignore if you don't know the these are the neurons, this is the memory location. So there actually we are doing repeatedly matrix multiplications, convolutions, and there are some other worker there. So those things need to be done multiple time. For example, you have heard about ChatGPT. So in ChatGPT also it's a neural processing unit only. Like they need a neural processing unit only to run the model of ChatGPT, because that algorithm is written in such a way that there are a lot of matrix multiplication would be there, and therefore NPU are mainly designed to do those particular work only. But again, as I said, all the work, whichever things you do with NPU, can be done with a GPU and can be done with a CPU, and anything done by GPU can be done with CPU, and therefore the CPU got the name of general purpose computing. And only the con of using a CPU for your neural processing, and that is time. Now let me give you one example, and that is a chip which is released recently by Intel, and which is called your Lunar Lake, or which is also called Intel Ultra Series 2, I guess. Yeah. So they have CPU, because for sure it's a CPU only. They also have GPU in that SoC. It is actually SoC, system on circuit. It's not a process. It's not only a processor. It's a SoC, because it's have many other things. RAMs are there also there. I will go there later if required. But the main things it have a CPU, it have a GPU, it have a NPU also, right? And to decide how much AI capability your processor have, we tell something in TOPS, which is the units. Okay, so don't quote me anywhere, but roughly what they said, and that is NPU have 47 TOPS, GPU I forgot. For now, roughly take 20 tops. And for CPU, they said it can handle 5 tops. So which means which means that your CPU can also handle a little bit workload of your neural network or AI processing things locally, anything you do locally. For example, I want to blur my background. So it's actually a process of artificial intelligence because they are detecting the age of my things, right? So those kind, if it is a very minor or trivial job, then that can be done by CPU only because CPU have these 5 tops. So in a nutshell, this is what your CPU, GPU and NPU mean. And in this course, we're gonna design a general purpose computing, and as you know, your general purpose computing can do other work also. So therefore, if you know how to design a general purpose computing, you just need to increment your knowledge to design a CPU in future, GPU in future, or probably NPU in future. So we'll see where we can go. Now, anytime you apply, you're gonna apply for a role of RTL design, you might be seeing in the JD, in the job description, that you need to know about architecture, and also you need to know about your microarchitecture. And you might have some question what these two things means actually. So architecture, like we have different types of architecture anytime we design a processor or CPU. For example, we have x86. All the Intel based processor, all the AMD based processor are on x86. You might have heard about M1, M2 from Apple. So they are of ARM, or Qualcomm, or any chip of your mobile all are in ARM based architecture. There are other not so popular architecture also there, like MIMS, probably Spark, I guess. Yeah, but those are not so popular. Very popular are only x87 and ARM, right? So we know the name, but what does architecture actually mean, and how we decide on architecture, if we should go with x86 or if we should go in the ARM way, right? In simple knowledge, architecture is like you will decide what are the components you're gonna use to do processing. What processing should do, you have the specification. Also, we can say that it's the programmer view of the computer, because as a programmer or as a person who is developing some utility for the CPU, they need to know how many register you are using. Register means the memory locations. In your ALU, what other operation you are supporting, right? Controller, how it is controlling, what is the clock speed you are using, how many IO pins you have. So those are the things which are called your architecture if you combine them. Now, to select one architecture over other, there are a lot of dynamics are there. First dynamics is the performance, for what you are designing it, right? Then power, how much power you need. For example, you might have seen ARM based processors are actually more power efficient. Like all our mobile devices are in ARM because they are power, we need the power efficiency, right? Our Apple laptop are power efficient, you have heard M1, M2, because they are in the ARM based chip, right? So why something consume more power and something consume less power? If I want to give you one example in the architecture only, for example, your CPU consists of ALU which can only do addition. It can only do addition, nothing else. Now for doing addition, you have many choices. One choice would be you can just go for your ripple carry adder, right? Or you can go for your look ahead carry adder, or look ahead adder, I guess. I forgot that name. Look ahead adder, I guess. Yeah. So now your ripple carry adder actually use less number of gates. So if it is using less number of gates, it will use low power for sure. Your look ahead carry adder, I think, it is using a lot of resources. So if it is using a lot of resources, which means in the power scenario, it will use a lot of power. But the benefit we are getting, and that is that look ahead adder will actually do the same addition in very less number of time. So if it should be a performance based one, for example, if I want to design a server CPU, all the data center has a server CPU, and I want to design a CPU for my mobile, and both are doing addition, then tell me which one will take which architecture. If it is only doing addition, ripple carry adder or the look ahead adder. For sure, which for server performance is the main thing, so we'll go with the look ahead adder. And for the mobile one, performance is required, but again power is very important because it's running by battery, so we'll use a ripple current. So this is about architecture. Now what does microarchitecture means? As I said, x86 is the architecture, right? Now your Intel based CPU are also in X architecture and your AMD are also in x86 architecture, but you might see there sometime one of the CPU consume less power, some is more efficient, some is producing more heat. Now if the architecture is same, and I said architecture implied how many register, or in rough scenario, in broad scenario, how resource like what the strategy you are using to use your resources. Resources means memory location, registers, ALU, IO pins, right? So now if both are using x86 architecture, then why we are finding those differences, and why we have to define company actually, because they are doing the same work, right? So there actually come the concept of microarchitecture, and microarchitecture are actually the different flavor of the same architecture. So x86 designed by both two companies, but they might have their own proprietary idea how to arrange those particular registers or IO pins or other things, right? One may decide that hey, we will have 32 general purpose register. Other might say no, we need 64 general purpose register, and that will actually bring rise to your microarchitecture definitions. Now you might be little confused about architecture and microarchitecture. Architecture are defined by the instruction your processor will follow. So for Intel based processor or for AMD based processor, they will follow the same instruction. Mostly 90% of the instruction would be same. Instruction means add, multiplier. If one support add, multiply, division, then other will also support the same thing. Or other will be for adding, other will be also doing the same kind of steps as Intel doing or AMD doing. So both will follow the same thing. But in the hardware, how they are managing their hardware imply how their microarchitecture are, right? But if you go to the ARM, then probably their add steps, like if I want to do A plus B, then the steps include to do A plus B would be very different from a x86 architecture, or might be same also, but there could be a differences. And therefore we sometimes we find, for example, recently Qualcomm launched their PC, right? Their Snapdragon Elite, I think their Elite processor are coming in PCs, in computers, right? But we have hearing that many of the games are currently, as I am shooting it, many of the games are not compatible with their PCs. Why? Because the instruction or the developer of that game, when they are developing it, they have developed it for x86, and therefore that game are easily compatible with any x86 processor like in AMD or Intel based CPUs, because I said architecture means they are using most of the time similar kind of instruction. But because ARM is a separate architecture, which imply the instruction or the steps involved to do any operation would be quite different, and therefore each game developer need to see how they can port the same game or the instruction in behind, because it's a programming only, right? Behind the scene programming only. In next episode I'll tell you what does programming mean actually in processor. And this actually bring to us one of the very important topic, and that is CISC versus RISC. Actually we divide all type of architecture in two separate domain. One is called your CISC, which is called your complex instruction set computer, and RISC is your reduced instruction set computer. And if you have guessed, ARM is your in the reduced side and x86 is in the complex instruction set computer. And as I said, actually architecture are defined which instruction sets they are following, and microarchitecture how the hardware are being built, right? So x86 will follow CISC and your ARM will follow RISC. For example, there is another example, and that is RISC-V. You are hearing this a lot because RISC-V is a open source, and this is you need to get a license to design any CPU from ARM, right? x86 also like that only. Now as name suggests, CISC means complex, means their instruction set would be very complex. RISC is reduced, so they have a reduced set of instruction sets. But what's the need of doing that things? Need of doing that things because the Because in stage 0, how your hardware will look like are depend on how the instructions are. So if it's a complex instruction set, which imply there would be a lot of instructions. For example, you want to do, like your processor want to do this basic operation, plus, minus, multiplication and division. So to achieve this fourth thing, you can have 4 instructions, right? I can have add, I can have subtraction, I can have multiplication, and I can have division. Our ARM also want to do the same operation, right? But ARM will have, like, this is not I'm saying ARM is actually having, I'm giving you an example, so don't quote me anywhere that this is the theory. This is, I'm trying to make you understand. If you want to know more about this thing, you can read their LRM, I guess. They are freely available learning material to know all the instruction set differences. But the intention here to let you understand what is happening, right? So yeah, for our example ARM, or for example our own CPU which you are designing, probably we want to use RISC. So our own will have only add and sub, and using only these two only I want to execute these 4 operations, right? So therefore I have reduced it, add and sub. You might say, hey, how will do multiply, how will do division? We can do it, I'll tell you how. Probably few of you know already. So now what's the advantage? I'll come there, why we are reducing it actually. So here the main advantage is that for multiplication you only need to write one line, probably mul and x, you say x, a and b. So probably I am doing what I am doing in higher level, I am doing x equal to a into b, probably I am doing that, but I need only one instruction, only one line of instruction. But here, because I don't have a mul instruction set, so therefore I need to do a repetitive addition to execute the multiplications. For example, you want to do 3 into 10, which will result into 30. Because we don't have a mul instruction, so how we can do repetitive addition? That is, you do the addition like 3 plus 3 would be 6, then 6 plus 3 would be 9, and you will do the same addition for 10, and therefore in the end you will do 27 plus 3 and you will get a 30 result. Very important. Just concentrate here. Here we need to use our add instruction how many times? 10 times, or 10 lines of code required. But in the CISC side, only one line of code. One advantage for sure, and that is any programmer who are writing for CISC, for them it will be very simple to do or to develop any software. They only need to write one line of code. But for here, for ARM developer, it's really complex. In the name, complex is not there, but when they are coding it, it becomes a little complex. That is a disadvantage of ARM, a advantage of CISC. But you will see one thing, and that is this mul is there, therefore you need to decode it, right? So decode it imply a little more hardware is required. You have a division, so you need a little more hardware to decode that also. But in our ARM case, as we have only 2 instruction, the instruction register will have less hardware, or instruction decoder will have less registers. Less register imply less resources, which imply less power, and therefore ARM are like that is in a very nutshell we can say ARM is a very power efficient I can say processor architecture. Again, because you have 4 instruction here, now just imagine you have 1000 instruction, and compared to your counterpart ARM, you have only 400 instruction. So for 1000 instruction, probably there would be a huge your resource overhead. So it will become a little slower also, right? Because the hardware, the far the hardware are, to access anything from those hardware will take some time, because you have the routes, long routes. So routes will have the parasitics, which will have the delay. So CISC might introduce some delay there, but ARM would be quite efficient to work. But again, because ARM, for a simple multiplication, ARM need to do 10 separate decoding and fetching things and storing things. There are a lot of things going behind the curtain. So might ARM also need the same amount of time to do this. So therefore the microarchitecture define a lot of things, because without seeing the microarchitecture, we can't say that hey, CISC will take like would be quick, will be more efficient than the ARM or vice versa, or in the power sense also. Yeah, in a rough sense, for sure, most of the time ARM are very power efficient. You can see orders of instruction are very different. So in most of the time, ARM are, we can say, without seeing the microarchitecture only, that hey, they would be more power efficient. But in the part that who would be faster, who would be slower, we need to see the microarchitecture. Now there is very important question, and that is, what does mean programming or coding? This is very important because anything we write, I'll go there. For example, addition, multiplication in our coding, any coding, Python you can say, Java you can say, or C++. That things are being processed by your CPU or the processor. And as we are in a course where we are designing the CPU, so we must know the things actually, why we are designing or what we are doing in a nutshell, I can say. Let me take a very simple example, and that is this: C equal to A plus B. Probably this is a Python code. Any code like Python, Java, C++, C, those are called high level programming language because they can be understood by human, and these are mostly like a English only, like if else, these are like English only. But to achieve this C is equal to A plus B, the final objective should be that we should go something like, we should able to convert this to some stream of bits only, because we know our computer, our digital system can only understand 0 and 1. So how we do that? Because as a Python developer, we just write it and we get the result, right? So we have something called compiler. So compiler will compile this and will change it to what is called machine language. Now for this course, there is no prerequisite of machine language knowing, but if we have some idea of machine language or machine level codes, like assembly language it's called actually. Like we have one assembly language called 8085 or 8086. So most of the BTech syllabus, probably in my time at least, we had this course, and you have some time between week 1 and week 2 content. So you just take some time after week 1 content you have seen, then go through a rough idea of what those assembly languages are and how they are written actually. So if we compile this in our assembly language, then how the things will work? There are many architecture, but if I take an example of ARM architecture, then they tend to first load everything to your register, general purpose register. Again, what is a register? We will see when we will do the hardware implementation. So there we will have a memory locations, probably a shift register or a SRAM or something else which will work as a register, and that is called register. So here R0, our computer know, right, that what is R0. How they know, I'll tell you little later. So I'll tell that hey, A equal to R0. If I have another register, then I'll call it B, and if I have another register, 3 register, I'll call C, and then I'll call, and this is purely a assembly language. Here I am writing here, okay, and this is will be different according to different architecture, but mostly because it's simple, so it would be same across all the architecture mostly. But this is from the ARM, or you can say RISC perspective. So I'll say add R0, R1, R2, let it R2. So this is the line of code, and these lines of code actually will execute or help you to execute this C equal to A plus B. And for sure, writing any code in assembly language is a bit difficult as a human, right? And therefore we actually design a compiler, and compiler is like one-to-one mapping. Like in compiler, again we have some logics which will map one-to-one from, like how should we map this to this, right? So there are one-to-one mapping, or you can say in our vlsi design also we have synthesis, like we write the RTL codes and then we synthesis to gates. So it's something like that. You can call compiler as something like that only, like synthesizing. You are synthesizing your high-level codes to the assembly language. Now again, these things also our computer can't understand. I said na, computer can understand only 0011 those streams. So now I said one place that here we will be having a module where we will decide how to decode a instructor. So decode a instruction means here you have this add is a instruction. So probably we have some mechanism by which we will tell that hey, anytime you see add, you just code it to something like 101 probably, and we will do some hardware implementation where if it get 101, then it will send it to the particular hardware piece which will do actually a plus b addition only. And finally this line of code will actually convert it to a streams of bits only. And our task as in this course, and that is we won't gonna design a compiler, it's a huge things. We will take any ARM any assembly language and we will try to convert that assembly language into bits. How will convert? Using the hardware implementations. And hardware implementation is actually we will write in Verilog, because in Verilog it's very easy to design the hardware. Once the Verilog implementation of the hardware is there, then there is the RTL to GDS flow. If you know, RTL to GDS means from the RTL code only we'll get the hardware, the layout, and we'll send it to Foundry, and the processor is in our hand. It's easy to go. So that is our task actually, how to convert any assembly language to the bit stream. So in nutshell, this is the course structure here. So and to do that, here we are doing addition, so we need a ALU. We are doing the instruction decoder, so we need the decoder. We need to store the these things, right? So we need to like this instruction set, so we need to have a memory location or memory reader or memory operation, how to do those things. And as I said, we need to have the controller, because controller only know whenever data are valid, when A, B are coming, when they are valid, right? So we need to have a controller, and there are many other things like how to have the IO and deciding those things. So week number 2 gonna be interesting, because from week number 2 onward we'll start coding, we'll start practical implementations. Now we have done a lot of theory. From week number 2, first of all we'll see some block diagram first, block diagram or the architecture of our particular things which we're gonna design, the processor we're gonna design, what we need to decide on what all instruction set we should include in our processor, because there are instruction set like 400 instruction sets are there, but we can't design everything here, right? It will take a lot of time, lot of like our bandwidths. We want to learn the things, so therefore we will design a few things, and actually those few things only will help us to just extend our knowledge for the future. And we can easily, if required, we can do with more complex instruction set, how to decode, but the basic would be the same. So after this week is end, you can see below you will have quizzes, so you need to take the quiz. You need to get at least 75% of marks, and these quizzes are mostly from your prerequisites. So I hope you have already gone through your prerequisites. If not, you have still some time, go through all the prerequisites, and the week 2 content will be released by 15 October 2024. So if you are seeing these things after 15 October 2022, it's already available in our portal. So before seeing those, please go through, do your basics, and we'll meet in week 2 content. And something very important to this portal, and that is we also have a quiz, you can say interface, which is similar to, not exactly similar, but kind of similar to the screening exam you will take whenever you go for your placement in off campus also, and anytime you are doing in campus also, you need to give this type of exams. So there you will find a similar kind of interface. So my objective is that if you practice some exams like that before you do the final exam, which you're gonna write whenever you go for the placement, then it will be beneficial. So that is another perk of this portal, and the best USP of my portal, and that is it is super cheap actually. And you can see this course, this is all full free, it is available in YouTube also. The Verilog 2 is of 199, and I think we have some coupon code, you can go and you'll search. And this course which we are talking actually, if you have liked week 1 content, if you want to continue it for the full course, then you just need to pay not the 299 but only the 199, and you can use this YCPU coupon code. And from week 2 onward, actually we were doing a lot of interesting thing, one of the interesting thing, and that is designing your let me mute it, designing your schematics. So this is the schematics we are designing actually. It go through the week 3 also. So in week 3 actually we have finished all this design. We have explained each and every line why they are coming here, and then we started with our Verilog coding of each and every blocks here. And Verilog code also, you don't need to install anything, you can just do it using online tool which is called EDA Playground. All the overview, everything is given, and week 4 will come alive very soon, before 15 November. So if you go through all the course content, then lastly I'll help you to actually develop your own GitHub repository, where we will make the repository out of these course only. We'll take each all the codes from these, all the screenshot from these, and it would be a awesome GitHub repository for sure. So I'm very much excited to see you for all these weeks, also week 2, week 3, and week 4. And after completing this all the weeks, you can also send me some suggestions where I'll decide on some bonus content. So that's all from my side for today, and I'll see you very soon for another good topic.